I hope you slept well. I just do a quick recap of what we saw yesterday and finish the last bit that was left, and then we start doing something. So, just a recap, this was the intuition for how we do static analysis, bias, and interpretation. We also saw roughly the three-step recipe that we need to typically follow to develop a whole static analysis. We have seen the semantics, so essentially modeling all the clothes with their characteristics and prices and so on. And in there we saw a whole hierarchy of semantics, in fact. Find the slide again. This one, with the abstractions. So between each of those points in the hierarchy, we have this alpha. In fact, we also have the gamma, so we always have a Galois connection in here. And all of these are mathematical objects that we cannot compute. In fact, I didn't say it yesterday, but most of the time, the Galois connection, we have it only between things that we cannot compute. So when things work out nicely, we have occasionally Galois connections with abstractions that we can compute, but it's very rare. In practice, we don't have a Galois connection. So what we have seen yesterday was basically that depending on where we are in this hierarchy, we can prove different properties. So up here, at the state semantics level, we can prove state properties. Down here, we can prove trace properties, safety properties here, liveness properties here. And when we need to prove general program properties, we need to go to the collective semantics. The collective semantics, if you remember, was the same question here. The singleton set containing the elements, containing the program or the analysis you want. Okay, then we started seeing some abstractions. So the first one that we saw was this one here. So I added the concretization function here. So in general, we don't have an alpha here. So when we start going with the abstractions that we can compute, as I said, we don't always have an alpha. We do need the concretization, a way to map the actual object that we work with to the actual concrete counterpart. So I actually corrected the slides a little bit, so I added the gamma here because we actually do need to go back to the concrete to actually prove the property. Okay, and so I show you some abstractions. So for instance, we looked at the sign domain, essentially replacing values by their sign. And we saw that we had different operations that we can perform on the sign values. What I didn't show you yesterday was actually the concretization, so I just wanted to go over it quickly. But essentially, a sign value is represents a set of values. So the bottom element is is the empty set. The zero element is the set containing the value 0. Top element is the set containing all values, and so on. When you have a map from variables to signs, you essentially you're abstracting a set of memory states, set of environments. So when you concretize, you get back a set of environments that map the variables to a value that respects the sign, so it's in the concretization of the sign. And then for when you have a state, an abstract state at a particular label, you're abstracting states, concrete states of a program. So this is your abstract state, a label, and your abstract element. This maps back to a label and an environment, which is a pair, which is a concrete state. All good? I didn't show it yesterday. Yes?
So in this lattice, 0 is less than greater than or equal to 0.
Yeah.
Because the less than relationship is about containers, like in the set.
Yes, essentially. Sorry. Yeah. Yeah. They're also different from 0. You see, it contains all elements that are not 0, and so it's bigger than elements that are strictly greater or strictly smaller. Okay. The other abstraction we saw was the intervals. I also didn't show you the concretization here, but it's similar in the sense that now the intervals are mapped to the set of values within the bounds. And the rest of the localization works in the same way. Okay, then we saw the analysis on the example. It was still not good enough to prove the property that we wanted. We still had the false alarm, and so this is where we stopped yesterday. So we need to track more information. We need what we call relational domains. These are domains that track relationship between variables. And essentially, we have, instead of having concrete values, so maps from variables to concrete values, we have sets of constraints. So essentially, conjunctions of linear equalities that essentially restrain the set of possible values that variables can take. So these conjunctions of linear equalities are also called polyhedra. So this is the polyhedra subdomain. And the elements of this polyhedra are sets of convex groups. So operations are going to be, well, for the order, we just do an inclusion check. The join is going to be the convex hull. So let's say you have one polyhedra and this other polyhedra. The convex hull is basically the smallest convex polyhedra that contains both. For the intersection, you basically take the intersection of all the constraints. So you join, you conjunct all the constraints in the polyhedra. You get a smaller polyhedra. The assignment is essentially performing an affine transformation. So let's say you have this polyhedra here. You're modifying the axis, this axis here. You modify x, so x now becomes x plus 1. Well, this moves your polyhedra by 1, essentially, along the x-axis. And for the filter, you have an expression. This expression is, let's say, a linear constraint or a set of linear constraints. You turn this expression into a set of linear constraints and you add it to your polyhedra, so you add more constraints. And this is, again, a possibly infinite set of elements, so you need a way to enforce termination. We will see it in the example how this works, but essentially, the widening, instead of doing the convex hull like this, whenever there is a constraint that between different iterations of your instruction is unstable, it will get removed. So you get a larger polyhedra. Yeah.
Sorry, what is an unstable constraint?
I'll show you it in the example, but let's say you have a polyhedra where you are, it's similar actually in a way, it's similar to the one of intervals. Let me go back to it, sorry. You see here, so let's say you have x is between 0 and 1, so you have linear constraints that restrain x to be between 0 and 1. At the next iteration, you have linear constraints that restrain x to be between 0 and 2. Now the x greater equal than 0 is stable. It's the same constraint between iterations. But the x is smaller than 1, smaller than 2 becomes unstable. And so as here we essentially remove it, in the polyhedra domain is the same. Except that now we could have constraints, let's say x plus y is smaller than 1. And then x plus y is smaller than 2. And now this one gets removed. And so you get, you can expand in multiple directions. But yeah, roughly the same equation. Okay, so too many animations. So let me go back here. Okay. And so concretization then. It's a bit slightly simpler or not, but essentially you have your convex polyhedra, a set of constraints, or you just map it to the memory states within these constraints, within this polyhedra. And for the states, it's as before. All good? Yeah.
So is it like each variable has a corresponding polyhedra?
No. Here there is one polyhedra representing, constraining the values of all variables in your file. I'll show you in the example it will make a bit more sense. This is the same program we're completing the modulo, and we still want to prove that we always, the state property here, where r is always greater or equal than 0. So we start again at program point 3, which starts with that interesting. So here the polyhedra that we have basically says that a is greater or equal than 0, and b is greater or equal than 0. At the next step, we add a constraint that says that q is equal to 0. This is because of this assignment here. Next step, we add this other constraint that r is equal to a. Here nothing happens, we just move from here. Now we have this guard to move to level 7. So R is greater or equal than B. So we have this constraint now. Now we have this assignment. This assignment is saying, where we basically say that R is equal to R minus B. We know that R is greater or equal than B, so R minus B is greater or equal than 0. This will be derived from the, essentially modifying the constraint with the assignment. Q is increased by 1, so we get Q equal to 1. And then we have to go back to 6 and do the join with what we had at line 5, at point 5. So what we had at point 5 was Q equal to 0 and R equal to A. What we get here is then basically, well, we still get a greater or equal than 0 for R because A was greater or equal than 0. So this, for R, nothing changes. For Q, we get the range 0, 1. And then we continue like this. So here we add again the constraint that R is greater or equal than B, which modifies this constraint here. We do this assignment again, so we go back to R greater or equal than 0. We increase by 1. So now Q is between 1 and 2. And now we have to do the join and widening. So you see here, we are in the case where the constraint for the upper bound of Q is unstable. That's why we just forget it. So we just keep the lower bound, which is stable. And if we continue like this, we see that this is a fixed point. Okay, I'll just, yes.
Why is the lower bound stable?
Yes, so here is 1, but when we go back to 6, you have to do the join with what you had at point 5. And at point 5, you have Q equal to 0. When you join it together, you get the complex hull, and the complex hull will do 0, smaller equal, greater equal than 0, smaller equal than 2. Yes, 1 second, I'll get it.
So sometimes the interval seems to just grow by 1.
Yeah.
And then we're just like, actually, we'll just go to
Yeah, because we see that between iterations, this is growing by 1, growing by 1, growing by 1, and we just extrapolate and say, well, okay.
Do you use the label to make that decision, or how do you know that you're not being too eager? Like, what if it just grows by 1 twice and then it keeps...
Yeah, you don't know that. So you're just going and saying, well, it could be that you're over-approximating too much. In fact, there are various techniques to make this less of a rough guess. Sometimes you can delay the application of the widening. You can wait a few more iterations to see if it stabilizes without the widening. Sometimes you can do widenings that are smarter. We will see it when we get to the termination part, that widenings need to be smarter than this. Yeah.
In line 7, I guess you sort of lose the premise that R equals A.
In line 7, up here?
Yeah.
You don't necessarily lose it. So here you know that R is equal to A, and A is greater or equal than 0. And here you add the condition that R is greater or equal than B, and B is also greater or equal than 0. So essentially, the fact that R is greater or equal than B somehow subsumes. You could keep it around, actually, if you want. But it's not going to be true after when you modify R to be R equal to minus B. So it stays there, but then it will just go away at the next iterations, in a sense. You have to, or it's solved?
Somebody asked it.
Okay, good. Okay, so we get to the fixed point here, and so then we exit the loop, we get to the end. And now if you see all the constraints that we always have that R is greater or equal than 0, even here because A is greater or equal than 0. So this is good, is what we wanted to prove. So now we have an abstraction that is precise enough that we can actually prove the property that we want. Okay, so in this part, I didn't want to tell you more about, there are many more numerical answer domains that you can study if you want. There is a very nice tutorial that Antoine Minet wrote on this, if you're interested in more. For what we need afterwards, these 3 domains are enough, essentially, for now. I just want to say a bit more about static analyzers today, in a sense. So we have, this one is basically maybe the most successful one, I would say. This was developed by Patrick Couzeau, Radia Couzeau, and Antoine Minet, Xavier Rival, and so on. The PhD students at the time at ENS. And it was a collaboration with Airbus. So they have done a static analyzer that actually works on control command software for aircraft. And this was then commercialized by Absinthe. So it was bought by this German company, is commercialized. And now is used actually in many companies. So still used by Airbus, used also by Bosch and all these other companies. So this was a sort of an academic success story. There's, as I said, software companies that are developing static analyzers. Meta is one of them. Developed this Infer tool, static analyzer, used by all these other companies here. If you want to develop your own static analyzer, there is this nice open source library for numerical domains. So here you get all the numerical domains that I presented and more already implemented. You just have to develop the engine that uses them. So all the operations that Polydra offer, they are all in there. You also have other domains. You have this weakly relational domain that is called octagons, where you have relationship between only two variables, pairs of variables essentially, and other kind of features. Okay, so now I can get to the part that I wanted to do today. So here we do safety properties. So we stick to this easy part here. The properties that we can verify essentially by exhaustive testing. It can be falsified by finding a single finite execution that doesn't satisfy the property. And to make it a bit more interesting, we will look at safety properties of machine learning software, just because it's friendly. And why do we care about machine learning software? Because more and more we have machine learning software in high-stakes systems, how we call them. So safety critical systems, or also systems that have an impact on our life in some way. And there are various reasons for this. So first of all, with machine learning software now we can do things that we couldn't do before with explicit programming. So you can imagine, you don't have to imagine, they're actually looking into this. When you have self-driving cars, was the first thing, but actually in the avionics sector, they're looking at image-based operations, like image-based taxiing, takeoff, landing, all these kind of things, all powered by machine learning. Not unsupervised, but still. They are very useful because they allow new functionalities on aircrafts that we couldn't have before because they can act as surrogate models. Essentially, there are often some very large pieces of software that perform some operations that are interesting, let's say braking distance estimation or these kind of things. These are, the software that performs this kind of operation is too big, it doesn't fit on an airplane, on the space that we have for software on an airplane. But if you put a neural network surrogate, this fits. And so this is interesting for the avionics sector. You can have more functionalities now if you implement them with machine learning. And then in general, you can automate decision making using machine learning, so you can save money. Problem is, when things go wrong, they can go very, very wrong. These are all kind of news, in a way. There was a recently robot taxi that dragged a pedestrian because it didn't see the pedestrian. So it was 2023, I think, and they are paying a lot of money now to the person. There were other cases where machine learning showed bias, so less safety critical in a way, but still an impact on people's lives, showing bias in criminal justice, in hiring, and all that. So for all these reasons, there is a lot of interest now from the formal methods community to looking into machine learning software. So I just want to tell you a bit more about these things. And as a simple, so there is a lot that goes on in this space. I will just focus on simple models for now, so which are neural networks that are feed-forward, fully connected, and that use radar activations. I'll tell you, if you don't know what they are, I'll tell you in a second. But essentially, neural networks are a bunch of nodes connected by edges. They're organized in layers. There is an input layer that takes inputs from outside. Let's say image takes the pixels of an image. There are hidden layers that do some computations, and then the output layers that produce some results. We're going to consider classifications, so classification models. So we're going to have one class for each class in the classification. So here it's a binary classification. This is an okay or not okay output. So the inner layers, essentially what they do is they take the values coming from the nodes in the previous layer, they do some sort of a fine transformation of it, and then they apply an activation function. The activation function decides how much of this value goes through, essentially. So here we consider value functions, which are essentially a max function. So whatever value we get here with this affine transformation, if it's negative, this is just reset to 0, so nothing goes through. If it's positive, it's the identity function. Everything goes through. At the end, when we get to the output, the value, the node in the in the output that has the highest value, this is the class that the input is assigned to. And since I like programs, you can also see neural networks as programs in a way. So this is an example that we're going to use in the rest. Well, it's sort of a variant of an example that we're going to use. So we have 2 inputs, 2 hidden layers with 2 nodes each, 2 outputs. So we can also write it as a program like this. This is a sort of a Python-like syntax. So I'm not being consistent with the syntax you have seen yesterday. So we read inputs, we apply transformations, we apply the value, this is the first layer. Second layer, again, the affine transformation, value function. Last layer, affine transformation, and then we see which one is largest than the other. We can ignore the equality case, that's just very rare. Once we do that, well, you can have your maximum trace semantics, right? And then you kind of know where you want to go, what kind of properties you want to prove. You go higher or lower in the hierarchy of abstractions to prove the properties you care about.
So, I'm something confused at what are the practical purposes of maximal trace semantics if you know like the initial states? Like, what is the added bonus of using maximal trace?
Well, let's say you want to reason about termination. You need to model the infinite executions as well. You need to deal with them in a way. And in all of the semantics that are in higher abstractions of this, you don't have any of them because you throw them away in the first step of the abstraction. So if you want to prove about liveness properties, you need to go down here. For all the other ones, you don't care. You can stay in higher levels. That's why most of the time you are at the top of the iceberg, looking at safety properties or state properties, all these kind of things, because you don't need to reason about infinite execution. You can just sort of ignore them in a sense. So yeah, for now we don't need it. I'm just saying, well, this is the general starting point. We can go higher in the abstractions depending on what we want, and it's going to be fine. Okay, just a notation for forward. Where you have an execution of a network, a trace, T, I will write T0 for the input, whatever is fed to the neural network, and TW for the prediction, the classification, whatever the input is classified to. Okay, so we're going to look at 2 properties. Essentially, they are both safety properties, but the first one is a particular instance of a safety property. Sometimes it's called robustness. I prefer the term stability. Essentially, what we're going to prove is that the classification is stable against adversarial perturbation of the input. And safety is general safety properties of a neural network. If I have a certain input, this is the output that I expect. Okay, let's look in stability. So, in particular, we're going to look at prediction stability. So we want the prediction of the network to be stable, more precisely. Whatever input perturbation we feed, so we have an input classified in a certain way. If we perturb the input, the output should still be classified in the same way. So as an example, I should add these pictures to the pets. Triangles like these are where my cat and dog. They're not live anymore. They're old pictures. But so let's say you have a network classifying cats and dogs into cats and dogs. And now you have a picture of a cat that is correctly classified as a cat. If you change the brightness of this picture, you still want this to be classified as a cat. If you change the brightness of a dog picture, you don't want this to be now recognized as a cat. So here, it's okay, we are stable, or robust if you want, and here we are not. So, we're gonna go through the same 3-step recipe that you've seen before, just a bit faster on this part because you've seen it already. First step, we need to formalize properly the property that we are trying to prove. And in particular, we're going to focus on perturbations that are distance-based. So let's say we're going to have an input, x, this is going to be an image, let's say. So this is, we define what is called the neighborhood of an image, x. And the neighborhood is basically all the other images that are at a certain distance from the input image. And the distance is limited by a threshold epsilon. So as an example, for instance, most common is this L infinity distance. So you have all the other images, you take the maximum of the pixels, the difference of the pixels, and this is smaller than a certain epsilon. Okay, if we have this neighborhood, then we can define the local prediction stability as a property. So the set of elements that satisfies the property. This is going to be, in the general case, a trace property. In practice, it's also a state property, but it's similar to see it as a trace property. So this is our property, prediction stability. It's the set of traces that are finite, obviously, because all neural network programs terminate. We don't care about infinite executions here. We start in an input that is in the neighborhood of our image x. This image is classified the same as x. Okay, so whatever perturbation we have in this distance, at a certain distance to the image, they're all classified in the same way. As an example, we can consider this network. This was an image with 2 pixels. The same structure as before, I just simplify the weights. So we have 2 hidden layers with 2 neurons. We have one output that are dogs, one output that are cats. So if I can consider this image here, so pixels are going to be between 0 and 1. This one is obviously, you can see, everyone can see that this is a dog. And now we're going to consider perturbations. The pixels are supposed to be between -1 and 1. But the perturbation that I consider limits the pixel to be between 0 and 1. Okay, so now I'm perturbing whatever image here. We have an input to consider all possible values of pixels for these 2 pixels to be between 0 and 1. Good, so concrete semantics. And you've seen it already, in fact. Which one are we keeping? Yeah, it's a safety property, so we can stick to this prefix trace semantics here. So essentially, the way we can prove the properties is say, okay, this is, in the general case, being a trace property, we have to prove that the maximal trace semantics of our model is a subset of our property. Since it's a safety property, we can actually consider prefixes, so only finite traces of this, and limit ourselves to that. So all the prefixes that start in neighborhood of the x that we consider, they should be a subset of the trace semantics. This is for the concrete. We don't compute anything yet. The other thing was... okay, no, that's fine. Now for the abstraction. The abstraction is going to be quite easy, in fact. We just have to do an abstract prefix trace semantics. The idea is we're going to start with an abstraction of our neighborhood, using whatever abstraction we want, intervals for instance. We're going to do the forward reachability semantics, if you want, some forward abstraction of our model, so manipulating all the operations using whatever abstraction we want. We're going to get an abstraction of all the outputs. So here, essentially, we are evaluating what the neural network is doing for all images in the neighborhood of the image that we care about, if you want, in a sense. When we get to the output, we have an over approximation of all the possible outputs, all the possible classifications of these input images. Now, if they're all classified the way that they expect, then we know that this is stable. This is local, with respect to a single image. And otherwise, we have an alarm. So we have this implication. So we have the soundness, but not the completeness. So it could be that the network is stable, but the abstraction that we have doesn't allow us to see it. I'll show you some example in practice how we do it, starting from the intervals that we have seen already. So in our example, the intervals, basically we are mapping the neurons here in our network to a range of values. So essentially, we just collect all the possible ranges of values for the neurons in the neural network. So at the beginning, we said the pixels can be between 0 and 1. So these are the ranges assigned to x00 and x01. First layer. Here, this is a linear transformation, so whatever value we have here is multiplied by the weight 1, plus whatever value we have here multiplied by the weight 1, plus the bias 4. So this is the linear transformation here. We do the operations using interval arithmetic. This gives us the interval 4, 6, and now we have to apply the ReLU. The ReLU, it's a max function. Here, everything is positive, so it remains the same. Now we do the same for x11. Now the weights here are 0.5, 0.5, the bias is 3. So here we have 0.5, 0.5 plus 3. This gives us the interval 3, 4, which is all positive. The ReLU remains. It doesn't do anything, it's the identity function, so it's 3, 4. Then we continue with the rest. So now x20, we get to the interval 17, 24, x21, 0, 3, and so on. At the end, what we get is the range 0, 10 for dog, and the range minus 4, 4 for cat. Now remember what we wanted to prove was that we always get the dog. So we wanted to prove that this value, the value of this node here, is always greater than this one. But this is not the case here, because the lower bound here is 0, the upper bound is 4, so there is an overlap. So there could be cases where the value of this node is actually larger than this one. Let's say this one takes the value 0, this one takes the value 4, then the output will be cat instead of dog. This is actually a false alarm. It's not true in practice. This network is stable, but we cannot see it. So again, we do the refinement of the abstraction I was seeing yesterday. We do a slightly more complicated abstraction. The abstraction, this is another abstraction that exists. So we track, it's called the symbolic domain, sometimes it's called, I don't know, constant propagation, whatever, it doesn't matter. This is one paper where it was proposed at SAS 2019. I think there were other papers almost contemporary that proposed similar things. But the idea is basically for each neuron in the model, we maintain a complete values, A and B, plus some linear combination of the input and also the previous values. Previous undetermined values, I'll show you what it means. But essentially, we have a symbolic expression that represents the possible values of this neuron. When we have the symbolic expression, when let's say